Hi students, in this video we're going to be looking at global wind and pressure belts. This is one of the topics that many of you said seems confusing, and certainly it is complex. The diagram that you see here on the slide, and by the way, if you missed the text, you don't need to be taking notes on the text as I'm speaking, but you can always go back to the online lectures, and this is from chapter 5. We are looking at an idealized model of global wind and pressure patterns. Excuse me. Because as with everything that we discuss with weather, we are looking at we're trying to gain the most basic understanding, but in the real world, these processes are much more complex. But we have to start somewhere. So I know we can look at this model and say, what? It's more complex than that? But actually it is. So this is the idealized model that excludes the effects of ocean, continents, and seasonal variations. Your textbook has the wind and pressure patterns as they really appear, but we don't have to worry about that too much, with the exception of some very influential patterns such as the monsoons. So what are we seeing here? If we imagine a seasonless, featureless Earth, in other words, there are no mountains, there's nothing that's going to alter the direction of winds and that sort of thing, we'll start with our surface heating at the equator. So we know the sun is more or less always or very near being directly overhead at the equator. It's between 23.5 degrees north and south. So the surface heating in this area causes air to rise. It increases the pressure at the surface. So you get those molecules very active as they're heated, and they rise. And this creates low pressure at the surface. As this air rises from the surface, it cools. And as it cools, it becomes more dense, and it will sink along or around the 30-degree north and south latitude lines. Now, where this air descends into a high pressure, because remember, descending air produces high pressure, we call these the subtropical high. So along 30 degrees north and south, you have your pressure belt known as the subtropical high pressure belt, and those are in both hemispheres. In this area, winds are frequently calm. If you're in Southern California, you know that this is the case because this is the dominant pressure pattern that you have here, pretty much subtropical high, where you get a lot of sunshine and usually winds are calm. These two convection loops that form as air rises above from the equator, more or less, and subsides at 30 degrees north and south, produces this conveyor belt type of pattern, which are called the Hadley cells. So you have one in the northern hemisphere and one in the southern hemisphere. And again, those rotate from 0 to 30 degrees, between 0 and 30 degrees. As this air moves back toward the equator, toward the equatorial trough, it converges. And as these winds do the same here in the southern hemisphere, where these two winds are coming together, you have what's called the intertropical convergence zone. So say that 3 times fast. No. But easier way to think of it is the ITCZ. But that's what it stands for. It's where the northeast trade winds that are coming out of the subtropical high and the southeast trade winds that are coming out of the subtropical high. Remember, the winds are named from the direction that they come. So these winds are coming out of the southeast. These winds are coming out of the northeast. And where those two converge is your intertropical convergence zone. And as we looked at in chapter 6, one precipitation mechanism is convergence of two air masses. So this will result in winds and cloud formation and a lot of precipitation. And between 30 and 60 is where you're going to get the majority of your variable weather. Here, yes, along the intertropical convergence zone, we're going to see weather. You can expect thunderstorms, you can expect showers and things like that. But it's not the more extreme seasonal variation that you get in the mid-latitudes between 30 and 60 degrees. So here you have the westerly winds. Again, they're coming out of the west. Same here with between 30 and 60 degrees north and south. The westerlies, for those of us here in the United States, really, really play a very important role in our weather and with the production of the mid-latitude cyclone, which we'll get to soon here. So this is a complex zone of conflicting air bodies where you have the easterlies coming out of the poles, the polar easterly and the westerlies, where those are converging, you have the polar front. And this will migrate seasonally, giving us those mid-latitude cyclones here in the mid-latitudes. Some other things that you see on this diagram are what happens at the upper levels of the atmosphere. In the mid-latitudes, you have upper atmosphere westerlies, and you see how these are not influenced by friction, and they're very fast moving. So there's no topographic feature here to change or alter the course of the direction of these westerlies. And more toward the equator and the tropics, you have the anti-trade wind. So at the upper elevations, upper altitudes, you have anti-trade winds in either direction, north or south of the equator. So those run in the opposite of the trade winds at the surface. Important also with our global wind belts are our upper level winds. So we were just looking at some upper atmospheric activity with winds. So air moves not only at the surface, but also at the higher levels of the troposphere. And one important feature here, and probably something that you hear a lot about when you watch the weather report, is the jet stream. And what is the jet stream? It's just a stream of fast-moving air aloft. If you fly frequently from west to east, you can catch the jet stream and you will move very quickly, and oftentimes your flight will arrive early when you get to the East Coast. But if you're flying in the opposite direction, you are flying against the westerlies, and so it takes a bit longer, takes a bit more power. So they occur where the pressure gradient is strong, and remember that's where you have a significant difference between the high and the low pressure. What happens, and what we talked about in the previous slide with the air masses in the mid-latitudes giving us the most variable weather that we see globally, the jet stream plays an important part. So here you have the jet stream at the base of this polar air. And sometimes you hear about an Arctic blast where this mass of polar air, whose boundary is the jet stream, can actually migrate more to the south than it usually would. And this starts to create a meridional flow, where here it was just more true east-west. Now you have more north-south meridional pattern with the jet stream. And this pattern here, this type of wave is called a Rossby wave. So that's more between 30 degrees north and 30 and 60 north and south. It is not the same as the Hadley cell. Hint, hint, this will be important for the midterm. The Hadley cell is between 0 and 30 degrees north and south. So the changes that are brought here by the meridional flow, the migration of this cold polar air mass to the north and south plays a big part, and where the jet stream is. Here you will have obviously warmer temperatures, and here you will have more of North America experiencing colder temperatures. So the Rossby wave here and the jet stream are also important to wind and pressure patterns. Okay, that's it for this video.